All right, our next speaker will be Zhicheng Zhang, who will be talking about a quantum register machine, and we'll just give him a minute to finish getting set up. And cool. Hopefully the screen is about to pop up. All right, take it away, Zhicheng.
Cool. Thanks, Robert, for the introduction. I'm Zhicheng, and I'm going to talk about our work on quantum register machine, efficient implementation of quantum recursive programs. And this work was done in collaboration with my supervisor, Mingsheng. Let's start with the question why we consider quantum programming. So this is just like the classical PL. It serves as a bridge between the human and the machine. And for the programmer, we have high-level quantum programming languages that provides you a convenient description of the quantum algorithms. And for the machine side, we can compile these high-level quantum programs into low-level quantum circuits, maybe through multiple steps. And the quantum circuit will be finally executed on the quantum hardware. So there are two goals we hope to achieve in this whole process. First, we want a high level to provide a convenient description for the programmer. And also we hope this compilation process can yield an efficient implementation of the programs. Okay, great. So why we consider quantum recursion? Maybe we should ask why we consider the classical recursion. And in the imperative programming languages, this is often supported by the recursive procedure calls. And one typical example of using recursive procedure call is the divide and conquer method. So you have a large problem, you divide it into several subproblems, and you call procedures to conquer each of these subproblems. And of course, the procedure you're calling can be the same as the procedure you are defining, but maybe with a different parameters specifying the size. So this allows you to encode very complicated computation in an elegant and compact way. And there are a lot of examples of that. Okay, so what's new in quantum programming? In programming, we have data and control flow. Of course, in quantum computing, the data can be classical or quantum, and here we just focus on the quantum data. And for the control flow side, we have two types of control flows in quantum programs. One is the classical control flow, and one is the quantum control flow. And the quantum control flow is just the superposition of program execution. So it is often guarded by the so-called quantum if statement, which compared to the classical if then else statement that conditioned on the Boolean expression. But here we are conditioned on a qubit variable, which can have this state being in superposition state. For example, you can write it as alpha kit 0 plus beta kit 1, where alpha and beta are complex number. And condition on the state of Q, you go to the first branch and the second branch, and they are quantum branch. And you execute both the branches together in superposition instead of going just one of the branch. And you can alternatively write out the unitary describing this qubit statement as a combination of controlled unitary for each of these branch. Okay, great. So once we have these two programming features, the quantum control flow and the recursive procedure call, we can arbitrarily combine them, and this naturally induces the quantum recursion. And there are also many examples of quantum algorithms that can be written as elegant and compact quantum recursive programs. And here I should mention that the recursion we are considered here is the most general form of quantum recursion. So you can arbitrarily interleaving these two programming primitives. That means when you are defining some procedure, you might define some quantum if statement inside, and it creates a quantum branch. And each of the branch, you can call other procedures. And in the definition of that procedure, you can also have internal quantum control flow. And you can, again, call other procedures, and the procedure can be done in a recursive like the linear combination of unitaries, Hamiltonian simulation, quantum state preparation, HHL algorithm for the solving quantum linear systems. And it is just a combination of this controlled UX. And there is a straightforward way to implement this unitary by taking the sequential product of this control UX. And obviously, this time complexity for implementing this straightforward way would be proportional to the summation of each Tx, the time complexity for implementing each control UX. There is also a parallel implementation for this quantum multiplexer, which can achieve a better parallel time complexity proportional to the maximum of Tx, which is exponential better than the straightforward way, but it comes at a price of manual design of complicated quantum circuit. So a natural question is, can we design at high level and still obtain such kind of efficiency? And this question, of course, goes beyond these specific examples because we are considering programming languages. Okay, so using the quantum recursive program, we can do it. We can describe the quantum multiplexer as a quantum recursive program in the language RQC++, which is defining our previous work. So here you can see the key procedure is this PKX. And in the procedure body that defines this procedure, we have this quantum if statement, which creates two quantum branches. And in each of these branches, we will call the procedure PKX itself, but with different actual parameters. Okay, you can see the interplay between these two features, and intuitively, this allows you to check these controlling qubits in a recursive way. So you are recursively collecting this control information, create exponentially many quantum branches, and then at the bottom layer, you just call each of the procedure QX for implementing the UX. Okay, what's good about these programs? First, it is elegant. Second, if you further have a way to compile this program and implement in some machine that supports this recursive procedural call and quantum control flow, then you can execute these two quantum branch in superposition together. So that means for these exponentially many quantum branches, the running time, the overall running time of this program will only depend on the longest quantum branch. That will induce a maximum of Tx. Okay, so now for our contribution in this work, we propose a comprehensive implementation process for quantum recursive program, and this is based on a new architecture called quantum register machine. It is an abstract architecture accompanied by an instruction set QINS and provides instruction level support for quantum control flow and recursive procedure call. And the implementation process go from you first compile high-level programs in RQC++ into instructions in QINS. Then at the instruction level, you can execute this compiled program by loading it into a quantum random access memory. But to handle the quantum control flow, we also need to do the partial evaluation. I will introduce it later. And then we can execute on the quantum register machine, and finally, this will be converted to quantum circuit. And if you analyze the final complexity for this implementation, it gives you some bonus of automatic parallelization. For example, for the quantum multiplexer program, it automatically yields a parallel implementations. Great. So for the architecture, here is quantum register machine, which works like classical CPU. So it will first store the compiled program into a so-called quantum random access memory, which is a quantum counterpart of the classical RAM. And it will fetch instructions in each instruction cycle, then decode and execute the corresponding instruction and move to the next instructions, just like the classical CPU. And we also have all these storage components becoming quantum. We have quantum registers, which consist of system user registers, and we have this quantum random access memory separated in several sections, one for the storing the program and for storing the quantum data and the stack. Okay, so here, how to handle the quantum control flow. Inspired by the previous work called Quantum Control Machine, which borrows some ideas from the classical reversible architectures, we put a program counter into a quantum register PC. So PC just points to the current instruction you are executing. And of course, it is a quantum register, so it can be in superposition state. It can point to many locations in this program section. So you can execute these programs in superposition. Okay. So what is a new challenge when you consider quantum recursion, not just the quantum control flow? Now you have recursion, and recursion will introduce some non-determinism. So here is a problem called synchronization problem. That's roughly speaking, if you executing a QIF statement, you create two quantum branches, and they might have different termination times. So if you want a single CPU to execute both branches in superposition together, you have to synchronize these two quantum branches. And you might have nested quantum branches created by this recursive procedure call, and you don't know how many of them. So you need to automatically handle this problem without changing the program text. So our solution is by partially evaluating the quantum control flow. And this step is independent of the quantum data. It only needs the classical input. And we can collect this result into a data structure called QIF table. And it will also load it into the QRAN to aid the execution of the final compiled program. Great. And to handle recursive procedure call, this is just like the classical, you allocate the call stack in the QRAM. And one important thing is everything here is quantum, so they can be in a large superposition state. These registers and QRAM, they can be quantum entangled. Here is an instruction set QINs, which is a set of instructions specifying what the CPU should do when you fetch instruction and decode these instructions. So most of them are borrowed from the classical reversible architecture, but here we introduce the most important part is we introduce two instructions for handling the quantum control flow. And these two instructions allows you to inherit the high-level structure in the high-level quantum recursive program. So you always keep this structure, you can track the entanglement, and that allows you to handle this quantum control flow. And you can write out the decoding unitary for implementing these instructions, decompose it into elementary operations on register and QRAM. Maybe I should skip some part of this implementation process. So first step is compilation, which just consists of 3 passes. Let's look at an example. So here is for the quantum multiplexer program. On the left-hand side is after the first pass, high-level transformation. So you just introduce some new variables to simplify the structure. And on the right-hand side is after high to mid-level translation. Here we focus on the procedure PKX. It is a procedure declaration. And so at the beginning, just like the classical case, we first initialize these formal parameters. Then we handle these classical assignments. And since classical assignments are irreversible, we need to introduce garbage data. And these garbage data will be automatically uncomputed at the end of the procedure body. And we also have these quantum control flows. We have this QIF and FIQ, which marks the beginning and the end of the quantum control flow. And you have these procedure calls, which need to operate with a stack because you need to handle recursion. Okay. Now, the key point is this part, the partial evaluation. So remember, our target is to automatically handle the synchronization problem. So on the left-hand side, you have these unsynchronized quantum branches. And if you want a single CPU to execute all these branches in superposition, you need to promise that they terminate at the same point. That is the synchronization. And the difficulty is introduced by the recursion. You might have non-deterministic number of nested procedure calls. So how to handle this problem? Actually, you need to use the feature of the high-level programming languages, RQC++. Once you have the classical input, but you don't need to know the quantum input, you can already evaluate and calculate the number of steps for number of instruction cycles for each quantum branch to wait for the other quantum branch. So you can, when you set the practical time tpreg, within this time you can partially evaluate the quantum control flow and collect all the information into a data structure called QIF table. So here is a QIF table, which is a data structure recording the history of all quantum branching. It is a graph, and in each node of this graph would be an instantiation of the QIF statement. For example, you go to this QIF statement, you create an instantiation of this node, then you might call do a recursive procedure call. You call the procedure again, and you enter this QIF statement again, and you will create another instantiation. So there are some nesting and non-nesting relation between these nodes. And when you do the partial evaluation, you only need to know the classical input, and you can determine how many number of steps I need to wait at each node to synchronize both quantum branches. Great. Finally, for the execution, we just load everything into the QRAN. including the compiled program and the partial evaluation result QIF table. And what the quantum register machine does is like the classical CPU. In each instruction cycle, you keep repeatedly doing this fixed unitary ucyc. And in each ucyc, you need to check the QIF table to determine whether we need to wait at the current instruction cycle. And if you don't need to wait, you do the execution. This is like the classical case. You do the fetch, then decode and execute, then unfetch and handle the branching instruction. And here's the decoding unitary where we just mentioned previously. It's a fixed unitary. Okay, and actually we can analyze the efficiency of the above implementation. It can use automatic parallelization for certain subroutine like the quantum multiplexer, and it automatically uses exponential improvement over the straightforward one. Okay, the final take-home message is quantum recursive programming can be win-win. It provides you both the convenient description and the efficient implementation. So you can try it in the design of quantum algorithm protocols. Finally, there are several future topics. This is just a theoretical framework for the compilation. So the immediate next step is the software implementation. And of course, we can extend the features of the programs. And there are a lot of optimization opportunities in this whole process because you have multiple steps. And also, there is an interesting question is whether we can obtain more algorithmic speedup from the programming language perspective. And here is an additional resource of a mini course I give on quantum recursive programming, and you can check the recording through the link. Thank you, and I am happy to take any questions.
Thank you, Zhicheng. Questions? Oh, good. I get to start.
Sure.
So, can you talk a little bit about the restrictions and limitations? Because there's all these problems. If we have quantum recursion, we could have a branch that goes on forever, and there's no reasonable way for me to implement that. I could try to control on the same qubit that I am trying to use. There's all sorts of things that can go wrong, and I know Charles Yuan talks about this in his quantum control machine, and Badescu and Panganen have talked about this a lot in their prior work. So yeah, tell me about the restrictions and how you get around these problems.
Thank you for this great question. So the question is about the limitation and the restriction of these quantum recursive programs and quantum register machine. So let's go back to the programming language. First, for the RQC++, here is just an example, but actually I prepare a syntax for the RQC++. Okay, so this program can only describe unitary operators. So here temporary doesn't consider the measurement, and this will make it consistent with the observation previously made in the quantum control machine paper. It is easier to handle the unitary when you consider the quantum control flow. Okay, so this is one of these restrictions, and another maybe kind of limitation is what you mentioned. You might have infinite loop. So actually, this is an unavoiding issue because in classically, you also cannot determine whether the loop will terminate, right? So here, actually, we set a practical time t-prac. You just check whether this program might terminate within this practical time. And I think this issue is it is hard to avoid these issues. Okay, these are two restrictions of the program and implementations.
Cool.
Thanks for the nice talk. I was wondering, in classical programming, there is this close connection between loops and recursion, like you can rewrite them. Can you do something similar here also, or can you comment on this?
Great question. So the question is whether you can converting some of the recursion into the loop, like in the classical case, you have the tail recursion and you convert it into the loop. My personal opinion about this is might be hard in the quantum case because you are creating multiple quantum branches using the quantum control flow. And when you try to convert it into a quantum while loop, like what is introduced in the WQS workshop by you, yeah. You need to so the quantum while loop. First, the definition might not be able, at least in this current form, to describe the exponentially many quantum branches, right? And in our case, when you do the recursion into two quantum branches, you might do different. You can call different procedures. So that means it will create more quantum branches. That makes it hard for describing into the quantum while loop. And of course, it might not be a tail recursion. It can be arbitrary recursion. Before the procedure call and after procedure call, you can have arbitrary things as long as follow this syntax.
Okay, thank you.
All right, let's thank our speaker again.
Thank you.